Welcome to the Crazy Hat Chemist. So another video in bonding. Let's get moving. Bam! So today we're talking about the hydrogen bond, but in water. Super cool. So look at all these water molecules, and they are hydrogen bonded to each other. So I'm going to show you a little model here. Okay, I have a water molecule right here, and that is the red thing there. That's an oxygen, and the two white things that I'm holding on to, those are the hydrogens. Okay, and the oxygen will hydrogen bond to a hydrogen on another molecule, just like that. Okay, and I got another one here as an example too, and they will just keep on hydrogen bonding. Notice that the oxygens and the hydrogens on another molecule will hydrogen bond to each other. Okay, and you end up with this really super cool structure here. Okay, that will keep on moving around. And that's a six-membered ring. That will be very important here in just a little bit here. So, okay, a hydrogen bond is a relatively weak, special dipole-dipole interaction. Covalent bonds are very, very strong. So there's my analogy there of that praying mantis of a covalent bond. And a covalent bond, actually a polar covalent bond, is between that oxygen and that hydrogen within this molecule. That's an intramolecular force. Okay, whereas that ant right there, who's going to win? That is an individually a weak ant. Okay, but in large quantities, in large numbers, okay, hydrogen bonds account for a huge, huge energy. So this is why they are very strong in number. So that praying mantis represents a polar covalent or a covalent bond, strong individually. However, if you have a tremendous number of hydrogen bonds between molecules, okay, like right here, then that can overcome that strong praying mantis, i.e. that individual ant can be totally consumed by that praying mantis. However, thousands or even hundreds of ants can take down that praying mantis, not a problem at all. Okay, so water can maximally bind 4 different water molecules. So I'm going to show you that to you here. So here's one water molecule, and when water maximally binds 4 other water molecules, okay, then what happens there is that this central water molecule that I'm holding on to will form a really unique structure, and that would be ice. Okay, when you hydrogen bond, when one water molecule maximally binds 4 other water molecules, that will form ice. And I'll show you a structure of that in just a little bit. Okay, liquid water typically contains between 2 and 3 hydrogen bonds per water molecule. It's rare that you would have 1 hydrogen bond per water molecule. Liquid water is closely packed. Okay, ice has 4 hydrogen bonds per water molecule. Okay, gas has no hydrogen bonds per water molecule. So here's gaseous water right there. It's not attached to anything else. So it's all by itself. Poof! All gone. Okay, whereas this water molecule has 2 hydrogen bonds. This water molecule that's in white there has 3 hydrogen bonds. So both of these white water molecules are going to be in liquid water. Okay, this one could be at the surface and attached to, like the container or something like that. This water molecule could be going into the gaseous state soon. Okay, this water molecule is in the gaseous state. Okay, that is not hydrogen bonded to any other molecule. It's not having any intermolecular force with another molecule. Okay, this is liquid water. Liquid water contains between 2 and 3 hydrogen bonds per water molecule with a constant breaking and reforming of hydrogen bonds as the water molecules move around. Liquid water is closely packed, it is random, it is very high in energy and entropy, and this is gaseous water, which has no hydrogen bonds with other water molecules. So let me show you an example of liquid water. Here is liquid water. So it is closely packed. Okay, and the water molecules are forming, and as I move this around, there are breaking and forming new hydrogen bonds constantly. Okay, that is liquid water. All the molecules are moving around constantly. That's opposed to gaseous water, which is poof, all by itself. Okay, And then ice, solid water, is a completely different structure, and it maximizes the number of hydrogen bonds that are formed per water molecule, and we'll talk about that. I am the Crazy Hat Chemist, and of course, I got a crazy hat here for you today, and thank you. There you go. Give me a thumbs up if you like that video. Subscribe to my YouTube channel, and I'm going to see you next time for more cool hydrogen bondings, but in ice. That's going to be cold, man. Bye for now.